Good morning, everyone. This is Jill Hurston with Synerzip. I'd like to welcome you all to our webinar today. I just want to remind you all that I am recording the webinar. It will be available along with the slides by tomorrow at this same time. You will receive an email from me with a direct link to the recording and to the slides. Please feel free to chat in any questions as we're going along, and our moderator will get to them as they come appropriate in the presentation. So with all of that said, I'd like to introduce Vinayak Joglekar. He is the CTO and co-founder of Synerzip. Vinayak?
Thanks, Jill. You almost promoted me. Good morning to everyone. Right. So this is 2018, and deep learning is not an esoteric topic that we would stay away from as in 2015 or earlier years. With the advent of new tools, particularly TensorFlow, deep learning has got democratized. So it's no more a topic that only a few data scientists would worry about. Today, deep learning is a topic that almost all developers have access to because of the democratization of the tools, and also the availability of cloud-based managed services where it is possible to handle a lot of data without having to invest a ton of money in hardware. So it's become more interesting because of the popularity and the ease with which we are able to make use of the algorithms and the techniques to solve problems. So today we are going to talk about a problem that we solved using deep learning. I was a part of it, and so was Krishna. So Krishna is our guest speaker for today, and I'll introduce him. So he has more than a decade, almost 12 years experience working with natural language processing. And he has worked on most of open source NLP libraries. He published a paper on sentiment analysis augmentation techniques in 2010 NACL. He created an NLP pipeline toolset and open sourced it for public use. And he authored natural language processing cookbook using Python. So with that, I'll quickly introduce myself. I'm Vinayak Joglekar. I'm a passionate software developer building software products using lean and agile teams. I've nurtured top-notch software professionals, and I'm actively pursuing business opportunities in big data analytics, machine learning, and natural language processing. Today's topic is of great interest to me because I have deep domain expertise in technical hiring, including resume processing, which is a problem that we are tackling today in today's webinar. And also I take and participate a lot in building software for technical assessment and interviews. So with that, I'll ask the first question for the starters. Krishna, can you tell us what is deep learning and how it is different from machine learning?
Hello, and a warm welcome to all the listeners. Thank you, Vinayak, for introducing me. And to answer your first question now, deep learning, machine learning, artificial intelligence. Okay, so the first thing that I would like to say is that they are all nothing but branches of the same tree. So artificial intelligence is a concept which goes back to early 50s, even 40s, 30s, 20s. I mean, if you can remember, we had the first artificial intelligence movie, or kind of a bot movie, which was released in Bollywood, called as The Day the Earth Stood Still, early 1950s sometimes. And if you ask me about my generation, then the Terminator series, it opened somewhere in 80s. So this concept is a very old concept. It's the idea, the ideation that happened for this. It is beyond any of us probably who are alive right now. So so to quickly come to to answer the question that you just asked me, that what is the difference between deep learning and machine learning. So these, as I said, the concepts already existed in the 70s and 80s. Earlier we used to call them statistical analysis. We will do the probabilities analysis and then regression and all that, and you will come up with smaller models for predicting stuff.
So what you're telling me, Krishna, is this is like old wine in new bottles, right? I mean, I remember doing ANOVA and cluster analysis and factor analysis in my college days, and we never used the term machine learning. And now I remember that, now that you're telling me this. So yeah, it does ring a bell. Yeah.
Absolutely, Vinayak. So as I said, with the advent of the cheap hardware and the advent of how the processing could be done faster and algorithms could be implemented and run faster, we have come into an era where a large amount of data can be processed in a very small time. So this is what has led to this transformation in usage of these similar concepts that have existed for like almost a century, and where we are right now, where we stand. So still, I mean, to find a difference between what exactly is the deep learning and what exactly is the machine learning. So think of machine learning as a statistical analysis tool that you had, where you are training a single equation using your independent variables. Okay, but where deep learning differs is that it has a layered approach in which you have feedback coming in from one layer to the another. Now, to talk about in the mathematical sense, it's like one equation is feeding into the next equation, which is feeding into the next equation. That's how the feedback is propagated. And that's how the final output is accumulated. And it's more refined, it's more precise, and the output is more better compared to your machine learning algorithms that you've been using. So that is the primary difference that I would say is between machine learning and deep learning.
And whenever we talk about deep learning, for some reason, I always think of neural networks. And for the benefit of audience, I'll just give a little bit of background about the way neural networks were conceived. So it's the way our brain works. So you have neurons that communicate with each other and they kind of trigger signals using axons, and which are connected through the synapses. So you have a kind of a set of neurons that trigger current, electrical current, and that goes, that is how our thinking patterns evolve, or that is how we recognize images. So it's the complex way in which our brain works is being simulated by this multi-layer processing that happens in what we call as a neural network. So what I can see in this picture that Krishna you have, and you can tell me a little more, is on the right hand side you have the picture or representation of a human brain, and on the left hand side you have the picture of a neural network as it is used for deep learning. So what are these different tools that you're talking about at the bottom, and can you tell a little more about what is ANN, and a little more about this?
Sure. So first of all, let me elaborate the acronym ANN. And ANN is nothing but artificial neural network. Now, when I say artificial neural network, as you rightly pointed out, on the right-hand side, we have the brain neurons and synapses, how they're modeled typically in a human brain. And on the left-hand side, you can see that there is a two-layer feed-forward artificial neural network. There is, kind of a similarity here. So essentially, these ANNs are designed to mimic the functionality of a human brain. That's exactly how they are trying to solve the problem, or trying to kind of formulate deep learning in today's world that we are trying. The implementations of these kind of algorithms, as you can see on the bottom, we have TensorFlow, Theano, Caffe2, PyTorch, Keras. There are so many such implementations available nowadays, and you can just plug and play and get your applications working and running with that quite easily.
Yeah, and we did it on our laptop. I would like to share, it's very exciting, and this coming up is the problem that we solved using. But before that, Krishna, this is all exciting, but can you tell us some typical problems that we solve using deep learning?
Sure. Vinayak, so the typical problems that you can solve using deep learning are the ones that are really not the machine learning algorithms that we had till 2010 were not able to tackle properly. So when you talk about the problems that we were not being able to solve, speech recognition, examples are Siri, Alexa. You're getting excellent responses and excellent communication with these chatbots that can recognize what you're speaking in any kind of an accent, even be it an Indian accent, African accent, American accent, English accent. Then you have the natural language processing problem. The kind of different kind of languages people use, the kind of words that people use.
And today's problem that we're going to talk about is mainly going to deal with text recognition.
Absolutely. Yeah. Absolutely. Moving forward, then you have bioinformatics. But the one place where these neural networks have really shown tremendous potential is image classification. So the problem I think till 2010s, we had these amazing search engines doing excellent job for us, like Google, Yahoo, Bing, and all that. But images was something that was still not kind of image search or image classification. That was something which is still lagging. But now we see that in this past decade, it has come up. So the reason why this has actually gone ahead is because of the advent of these artificial neural networks and how well they can work to classify images.
Yeah, and we have this classic problem of recognizing images of a cat or a facial recognition problem. So what it does is it goes through a series of passes. In the first pass, it would define just the edges. In the second pass, it would recognize the shapes such as circles, rectangles, squares, and then it would relate them to the cat's whiskers, eyes, ears, etc. in the third pass, and so on and so forth. And finally, it would know whether it's a cat or a dog, and it would recognize that image. So, for doing so, there must be some pre-processing or something that you have to do with the images. Can you just feed images of cat as they are, formulating, the mathematical model of zeros and ones with images of different colors, with different aspect ratios, with sometimes the cat is under the tree, sometimes it is running on the hill. So how do you pre-process or prepare the images so that you can? So can you tell a little bit about what is the preparation that you need for this? So do you work with color images all the time, or how does it work? So a little bit about that.
Sure. So as you correctly pointed out, the word is called as pre-processing. Mm-hmm. Any kind of a problem you have in the field of artificial intelligence, the training set that you may have, the data on which you're going to train your algorithm or train your equation, as we may say, there is always some amount of pre-processing involved, be it images, be it text, be it just plain statistical data. Now, since we are dealing with images here, I would like to say that, as you said, we do come across images which are sometimes different in color, different in sizes, different in aspect ratios, and their orientation of where exactly the object of interest is present. So yes, we need to do some amount of image pre-processing. In that, we do size standardization, that is scaling. So when I say scaling, then it may also mean that we are going to stretch or shrink the images to fit a particular size. Then there is a color standardization. That means sometimes you cannot work with colored images. If you want to just recognize a face, why do you need to worry about all the colors that are available in it? You can simply grayscale the entire image and you can easily find out the object of interest that you're looking for. And next is, as you said, that the object of interest may not be present at a very single position in each and every image. That means we need to identify where exactly is that image object present inside the image, whether it is on the bottom left corner, whether it is central, or so to elaborate. So this is kind of a typical example that if I wanted to recognize the face in this particular picture, then I have converted this colored image into a grayscale image. Mm-hmm. Similarly, if I have a cat here, okay, which is probably on a grass field here, mm-hmm. but I'm not really interested in what is behind or what is in front. What I'm interested in is only this cat. So what I've done is I've kind of masked the entire area where cat is not present, mm-hmm. and I'm kind of trying to highlight.
So you're removing the background,
yes.
and just keeping the, so
yes. And here
this is how you're labeling the cat in the picture of the cat, that this is a cat. I mean, that's how you're telling the training data. Absolutely. That in this picture, the cat is, the only thing that you see, the rest of the background is cancelling out by multiplying it by 0. And, the cat is the part where you multiply by 1 and keep that. So it's basically a layer of pixels, and you have zeros where the background is there and ones where foreground is there. So only those values of grayscale which are belonging to the boundaries of the cat will be read with their respective values, and those which are in the background would be multiplied by 0 and get cancelled out. So that's how you label the cat. So yeah, so that's how, and you have to take hundreds or thousands. How many images would you require to train an algorithm to recognize cats?
It depends on, actually it's a very good question. The better or the larger the size of the training set, the better is your algorithm, or rather the model that you fitted, mm-hmm. using your algorithm. Mm-hmm. Which means if I had 100 images of cats to classify, or rather to identify cats, compared to if I had 1,000 images of cats to identify a cat, the algorithm which has trained on 1,000 images is going to always outperform the one which has worked on 100 images. So yes, the more the training data, the better the results will be.
Mm-hmm. And there's a lot of talk these days about convolutions, right? Now, I heard this, that you run convolution. So there is this convolutional neural network, CNN, is what you use to solve image recognition problem, and that's how you actually recognize edges. And so can you tell a little bit about what are convolutions and how CNN is used, convolutional neural networks are used to recognize images of cats?
Sure, Vinayak. This is kind of, the perfect question, because as you correctly pointed out, convolutional neural nets, or CNNs, are exactly the ones that we use to solve image classification problems. Now, before we delve into what is a convolutional neural network, you need to understand what convolution itself is. Now, what is a convolution is, you take a small window, rather than a window, you can think of breaking the entire image into boxes, smaller boxes, mm-hmm. okay, so that you can understand So it's more like, break. So you have a bigger problem, a larger problem. You break it into smaller pieces, and you can solve it more easier, like how you solve your puzzles. So this is a puzzle, exactly. So how we solve it is we break it into smaller images. A convolution means you break it into smaller images, and you scan through each of the images, trying to understand the features that it has got, and you recognize the object of interest and you return it in your classification.
So in this, the image window is moving one window at a time, but in reality, convolutions move one pixel at a time, or do they move? Let's say the convolution is of 10 by 10. Would it move from 10 to 20, or would it move from 0 to 10, then 1 to 11, then 2 to 12? So is it a sliding window or is it a jumping window?
So as you correctly pointed out, the word is sliding window. So what a sliding window means is, as you can see on the screen, I have an image here, a test image that I've got, and I have a window that is kind of sliding from left to right and then coming down
sliding
again left
one
to right,
pixel at a time.
Pixel at a time, or 1 pixel at a time, or you can set it to maybe move at every 10 pixels at a time or 5 pixels at a time, depending upon the size of your convolution and also the size of your image and the accuracy that you are expecting or the images that you are kind of processing. Depends on a multiple factors, but that's how a convolution sliding window works. So yes, sliding window is the correct terminology that you use. And as you can see here in the example, as my sliding window moves from left to right and from then again bottom and left to right, it is finally able to identify the character 8 with 100% kind of confidence here, because it fits my convolution window perfectly.
Yeah, so this is you can say the classic image recognition problem that deep learning solves, and this is a good example. But for the benefit of our audience, I would like to introduce the problem that I had, which Krishna, you helped me solve. So since I came to you with the problem, let me describe the problem for the audience, and then so we have a number of resumes that we receive, and most of them are developers working in different technologies, and a typical resume will have basic information about the candidate, such as his name, his email address, his phone number, his objectives, an overview of his accomplishments, his education, his experience, followed by a number of projects that he has worked on. So there could be, say, 6 or 7 projects, and each project will have details of the designation and the roles and the responsibilities he handled and the kind of technologies that he worked on and the domain and the name of the company that the client for whom he was doing that project, the team size, and a lot of details about each project. And there could be multiple such projects. And in the end, probably you will find some certifications, some achievements, some hobbies and interests, and before signing off, the candidate may also mention his residential address. So that's the general structure that a resume has, but not every resume looks the same. Some resumes are using plain text, some are using bullets, some are using tables, some are having a lot of images and other things, some are in document format, a Word format, some are in PDF. So there is heterogeneity there, and there are practically unaccountable number of buckets in which you have to classify the text that you see. So there are different ways in which you can classify, or you can put the text in different classes, whether this is an objective bucket or a education bucket or overview bucket, or is it a project bucket? Within project, is it a responsibility? So there are numerous buckets in which this text has to go. So the problem that we are trying to solve is to make use of the data that is in a very amorphous kind of resume has to be made more structured by putting that text data into various buckets and recognizing things like how long the candidate was working on a particular technology, or has he not worked for a period of time in his life, or did he graduate a bit late, and things like that. So there are, and what if there is any missing information, that also needs to be flagged out. So all these things need to be automated, and for which we need to first parse the resume and objectively put the text in buckets at a very high speed, or maybe 100 or 200 resumes in a matter of 1 minute. So that's the kind of problem that we are trying to solve. So so this is a typical structure of a resume. For the benefit of the audience, you can take a look at this, and I'll let Krishna tell what was the approach, and how we approached it in the first place, and then we could talk about the solution. Yeah, so over to you, Krishna. So yeah.
Yes, Vinayak, as you said, this is kind of an outline of any typical candidate resume that you'll find in the technology industry. So if you look at, if you just pick up randomly any resume from a job portal, then you'll see that any candidate would have mentioned these, n number of different things, but they will all fit in under these top 8 kind of labels or buckets. So you can kind of parse the entire resume and put the content in one of these 8 buckets, and you would have probably classified the entire content of the resume, and you would not be left with any outlying text to save per se. So what are these top 8 buckets that you're talking about? So let me just go over it one by one. Full name, objective, overview, education, company experience, skill set, projects, and the footnote. Now they may not appear in the same order that we are seeing right now on the screen. Some people may write the projects at the end. Some people may write their objective at the end. Some people may, like to write their company experience at the top. So the order may differ a little bit here and there, but the content or the juice of the entire document can easily be passed and classified into these 8 top buckets. That's what was the understanding that we had, because we kind of had a huge data set that we were working with. So we had more than 1,000 resumes which were previously classified and which we could use as the training set, kind of the starting point from where we can build the entire solution.
We had, for the benefit of audience, so we had taken these 1,000 resumes and actually annotated each resume by highlighting and classifying the text that belong to one of these top 8 level buckets. But before that, we had also annotated by using some kind of gate natural language processing processor, what we call as a named entity recognition. So there are named entities such as first name, last name, then you have company names and technologies, and all those different low-level features, if you will, were recognized by transducers called japes, right? So, so the problem was half solved, I would say. And it kind of reminds me that you have a low-level feature such as a circle or a triangle, and then you have to convert it to a high-level feature such as a nose or a whisker or an eye. So you have these low-level features which were identified correctly, and then you had to process them further. So this actually looks like the image recognition problem, because you have low-level features which are identified using the first pass of gate or JAPE processing, where you call a city, a road, and a company, because that's what the name entity recognition algorithm will do for you. Once that is done, then which one of these features are assembled together in a particular fashion so that they form a higher level feature is the problem that we would like to solve, right? So how did we, is my understanding, is the similarity that I'm drawing between this problem and the cat problem valid?
You are actually correct. The way we modeled this problem, so just for the benefit of the audience that we have, the listeners, this is the overview of the solution that we had. So we had n number of CVs, as you rightly said. We processed them through GATE, which is a text engineering the architecture in which you can do named entity recognition, and you can also do your own kind of custom entity recognition stuff. And using that, we identified all these lower level features that you just talked about, not just, technology or first name or last name, but, as low as, how the data is organized in the particular document as sentences, paragraphs, where exactly are the anchors located.
And bold and italics.
Yes, bold and italic.
Yeah.
The edits that were done.
Right.
It's kind of physically how the document looks like. All those features are also recorded. And using those low-level features, the deep learning algorithm, when it is stacked correctly by the manual labor that we had here, when we got them to kind of tag them correctly to each of the buckets, then the deep learning algorithm can come in and learn from this and give us the required output that we were supposed to. This was the idea that we started with. So as you are saying that, there is some amount of similarity between the image classification problem and this resume classification problem, I absolutely agree with you.
It's a really manual process and a laborious process. We call these people annotators. These annotators actually went through each resume and annotated them in the high-level features that we talked about, so that we could get this training set of 1,000 resumes. So now, talking a little bit about how we proceeded. We have these resumes, they are annotated. Now, what do we do with that? Do we use all the 1,000 resumes for, how do we divide them into training set, test set? And, these resumes, do they require, like in the case of cat problem, we had to resize all of the images to a standard size by shrinking some of them or by stretching some of them, and then we had to remove colors and all that. Even in resumes, they are all of different sizes and lengths. So what kind of pre-processing was done on these 1,000 resumes?
So when talking about pre-processing, so it's also similar to how you model your data to feed into any given algorithm that you want to work on, be it a deep learning algorithm or a machine learning algorithm. So for that, as you said, we had, or rather the audience already know that we had 1,000 resumes which were manually classified by our annotators. We used this 1,000 resumes as a part of our training and testing set. We divided into a 70-30 kind of a bucket, rather size. So that's the norm usually you use. If you ask any data scientist, will tell you that whatever is the given data, you use part of it as training set and you use part of it as a testing set. The norm is that, you should use minimum 20% of your data as a test set, which is like, unseen by your algorithm, so that you can test the validity of your model's fit when you're done with training. So that's how we divided. We went with a distribution of 70 and 30. As you said, we did have to do some amount of pre-processing involved, which was, you just said that, as we kind of shrunk and also stretched the images. So here, what we had to do was, we could not have shrunk the resumes because we could not lose the data. So what we had to do was, we looked at all these resumes, what was the maximum size of a resume? And we realized that none of the resumes exceed more than 20,000 characters.
Mhm.
So we decided that we are going to stretch all the resumes to 20,000 characters because we do not want to miss out on any data kind of. So that's just out of the question, because this is a text that we are talking about and not really images. That's the difference we have here. And as we also work on, per pixel basis on an image to do image recognition, here also we decided that since the problem looks similar, we should work on per offset, that is, per character level, to solve this problem instead of, going at a kind of a larger level, like, a paragraph or a sentence or even a word. We decided that we'll rather work on each and every offset of this given resumes.
Yeah, so for the benefit of audience, an offset, let's say, is a number from 0 to 20,000, depending on where that character is in the resume, which is now standardized to a size of 20,000. So each resume had 20,000 characters, and each character had certain features, right? So can you tell what are the features? Like in case of a pixel, you have a grayscale value. Now, in the case of a character, what was that? What were the values, or how did you uh, assign a number or a set of numbers to a character?
So as we already saw that we had some entity extraction algorithms run on it, and also our annotators did a lot of annotations on it. So each and every annotation, each and every kind of distinct annotation that was done on any resume, that became kind of one feature for each and every offset, which means we had identified 98 distinct annotations or entities in any given resume. That meant that for each and every offset or each and every character in the resume, we had 98 features associated with them.
So there are these 98 features, like one of them could be first name, other could be email, the third could be a phone number, right? Now, so feature number 1 is name, feature number 2 is email address, feature number 3 is phone number. So let's call them, for the sake of this discussion, x1, x2 and x3 as 3 variables which will assume certain value. Now, if a character is belonging to a annotated first name, it will obviously not belong to an email, and it's obviously not going to belong to a phone number. So in which case x1 would be equal to 1 because this character belongs to first name. x2 is equal to 0 because it is not belonging to email, and x3 is also 0 because it is not belonging to a phone number.
Correct.
So you have 97 such features which are like whether it's a specific annotated feature like a named entity such as a city or a road or a technology or a particular name of a college or a school, everything, all the named entities were classified into these 97. Also, there were features such as paragraphs and bolds and headings. Everything was a feature. So that's how you could say that a particular character was a part of a feature or not a part of a feature by assigning a value of 0 or 1. Is this description of assigning value to a character correct?
Absolutely correct. You have correctly identified, how you do kind of a binary encoding for any given feature set on any test or training set. So this is exactly what we did. We had these 98 features, and we had a huge kind of a sparse matrix where there were a lot of zeros and very less number of ones. So we had to work with a sparse matrix. We decided to keep it sparse because, as we already discussed, that we did not want to lose any data. We always thought that losing. So yes, there were reasons for that. We did try to encode them differently. We used the octal system ones, and tried to kind of combine some of the features. We thought that maybe these features are independent of each other, so they can probably work independently of each other. We tried that stuff, but it did not really work out. So end of the day, I think it was more important that we used all the available information that we had and not miss anything. So that is exactly what we did.
Yeah, and given the fact that an email address cannot be a phone number, you could not have used something that could combine multiple features together, right? I mean, into a factor.
Yeah.
So it made sense to keep them independent. Were there any other feature like location which was not 0 or 1?
Yes, as you are saying, we did actually consider location as one of the features in our feature list, because we thought that even though the location of some of these elements, or rather the high level entities that we had, the top level 8 buckets, is kind of sometimes changing in the resume, but still it has kind of a location that people write their full name at the start.
Yeah, that's a pattern that I've seen.
That's a pattern. I mean, they will not write their name at the end of the resume.
Or not in the middle.
I mean, they have to give that information about themselves at the start. So we really thought that the location of these entities were also important. So yes, that was one of the continuous features that we had, and all the rest of the 97 features that we had were categorical in nature, 0 and 1.
So they were like the discrete 0 or 1.
Yes.
And there's only one feature which was like showing where it appeared.
Exactly. From 0 to 20,000.
From 0 to 20,000 as a range. And okay, so wonderful. So you have this thing. Now, before we go on to discuss further the kind of problems we faced, I think it would make sense, Krishna, for you delve a little bit on the concept of precision and recall, so that when we describe the issues that we had and how we solved them, I think the understanding of precision and recall would be important. So can you tell a little bit about precision and recall?
Sure, a very good question, because usually we have this tendency of measuring everything in terms of accuracy. Like how accurate is your solution? Please tell us. Now, what is accuracy? So say, for example, I have a machine which scans patients and tells them whether they are infected with cancer or not. Now, the amount of patients that actually have cancers is very less. So like, if you scan about 100 patients, only 1 or 2 patients are likely to, actually have cancer. Now, if I developed a machine which does nothing and just says by default that nobody has cancer. Now, in this case, even though I've missed those 2 people who were actually cancerous, but I did not, or rather my machine was not able to identify them, the accuracy still stands at 98% or 99%. Now, this is a very false kind of, the image of what my machine is doing.
Yeah, I mean, it's of no value.
It's a useless machine.
Yeah.
Right. So where does this precision and recall numbers come in? So this concept is more relevant to what your machine was able to identify as true positives. As in, so for any kind of a two-way classification problem, you have 2 classes. One is 0 and one is 1. So 0 is the one that you are not interested in, 1 is the one that you want to identify. Okay. So the precision and recall are working on that number, the 1. So basically it is, precision is a ratio of how many items that was selected are relevant. That means the ratio of correctly identified positive examples by the total number of correctly, or rather the total number of positively identified items.
So if we had said that out of these 100 patients, if 2 had cancer and if your machine had detected 2, its precision would have been 100%. If it had detected 1, it would have been 50%.
Absolutely.
Right.
Correct.
Yeah.
And when now moving on to the problem of recall. So the problem of recall. So what does this ratio indicate is that how many relevant items were selected. So that means if I had 5 patients that had cancer and I could identify all 5 of them, that means I could recall all 5 of them. So my recall ratio is 100%. That is 1. If I could recall only 2 of them, then my recall ratio is 40% or rather 0.4.
All right. So in my earlier statement, if I had 2 patients who had cancer and I had detected 1, in that case, the precision still would be 100%.
Yes.
But the recall would be 50%.
Absolutely.
Right.
You're right. Right.
Okay.
In
So
fact,
that's the difference. Now I understand that if I have all the all the true positives are identified in that case, and there are no false negatives, then I have 100% recall and 100% precision. But if I have some false negatives, right, in which case my precision is still good, but my recall is bad. And if I have some false positives, right, if I identify something as 1, but it's actually a 0, which is a false positive, in which case my precision takes a hit. My recall may be 100% because I could identify everything that is there, but in the process of my anxiety to identify everything, I went on calling some zeros as ones, right? So in this case of cancer patients, I would identify every cancer patient that had cancer, but also I end up identifying some otherwise patients who didn't have cancer as having cancer. So that's the, okay, now I get it. So precision and recall is a tightrope balance that you're trying to walk. Now, let's talk a little bit of what it has to do with the concept of underfitting and overfitting. So that's another thing that we keep talking about in machine learning. So can you tell a little bit about that?
Sure. So as you can see on the slide, I have a distribution of some problem that I'm trying to solve. It's again a two-way classification problem with 2 dependent variables and 1 2 independent variables and 1 dependent variable. So on the X and Y axis, I have my 2 independent variables, and this is how the plot of my samples looks like, my training sample. Now, if you see on the left-hand side, the leftmost side, it says that it's an underfitting model. So what underfitting model means is that my precision is not good, but my recall is high. So that means my model is a generic model. So, the more and more it is kind of, saying things as positive, but they may not be really positive. So to give an example that, if I had this kind of a data and I ran a linear regression on it, so then I get a model usually which will underfit, as you can see here. Now, on the right-hand side, the one that you can see is kind of an overfitted model. So now you can see that, the line which is separating these 2 classes is like, going all the way here and there, trying to...
Yeah, it must be
it's like force-fitting things.
Nth level, maybe a quadratic or something.
Yeah, absolutely. In terms of mathematics, I think, what algorithm will probably give me this kind of a solution is decision trees. So a decision tree, I can train it, to... And as you can see in the center, the appropriate fit. So now this is, kind of a curve which is
nice and
smooth, and it is still classifying my 2 classes quite accurately. Quite precise, and the recall is also quite good. Now here in this case, okay, mathematically speaking, who would be probably, which algorithm would probably do something like this better is random forest. I can clearly, I look at the shape of the curve and I can think that, okay, random forest is the algorithm that will be able to do this. Now, just for the benefit of the all the audience, this is, all too technical terminology, all statistical terminology. If I were to explain the concept of precision, recall, underfitting, and overfitting in, the human normal household life of any human being. So just an example that comes to my mind is that suppose that you're a guy married for 10 years, past 10 years, okay, and your wife kind of, on every birthday gives you a surprise. Okay? And one fine day, you guys are just sitting and having a nice wine and chilling on a weekend, and she just asks you, do you remember all the 10 surprises that I gave you in the past 10 years? Can you tell me which one? And suddenly, you're kind of in a first, okay, what will I do?
Thank God I don't have such questions coming up.
Nice one. So, yes, so all those people who, whose wives are not giving you surprises, you will actually thank me or thank us rather after listening to, what exactly will go on in a particular person's mind. So, you quickly come up with the 5 or 6 occasions when she gave you a surprise, okay, and you quickly tell all of them, okay.
Excellent precision.
Yeah, excellent precision, 100%. All 6 of them are correct. Now you are very happy that, I was very precise, but your wife is not very happy. She's like,
bad
you missed
recall.
out, man. You missed out the 4 or the 5 occasions.
Yeah,
what to do? So then the problem comes, you start guessing. And as you start guessing, okay, you may take more than 10 attempts.
Yeah.
Maybe even 15 attempts you made to
So
actually get to the 10.
Improve that recall, you are going to make.
Absolutely. To improve your recall, your algorithm has fitted a model which is very bad in precision. Now, your only 60% of your guesses are correct.
Yeah, your wife is still not
and
happy.
Your wife is still not happy. So, exactly, this is how, you kind of play a tightrope between that, okay, if you've identified 8 of these occasions correctly in your 10 guesses, you kind of, tell her that, what, I think I'm very sleepy, let's go and get some sleep today, we'll talk about it tomorrow. And you just end the conversation there. So this is the, the tightrope that you walk, basically.
That's the biggest takeaway of today's webinar for the audience.
Absolutely. All the married people out there.
Yeah. So let's now what this has to do with the problem at hand.
Yeah.
Now, like we were trying to identify projects. In first thing, I think we tried identifying projects, right?
Yeah.
And
then, so we broke the problem into, smaller problems. We thought that, let's not attack all the buckets at the same time, but instead, just try and identify only one of these top level buckets, just projects, and see how, our algorithm works. So as you can see here on the screen that, when we made the first attempt, our accuracy or rather our precision was very high. From the 8 projects that were present in the resume, we were able to identify 5 of them very correctly, but the rest of the 3, we completely missed.
So I was not happy.
Yeah. So then, so my, not wife, but my CTO was not happy. So that, what then that meant was like, I had to make a second attempt at it, and I had to generalize my algorithm more. And in that attempt, even though my precision went up, that is, I was able to identify all the 8 projects correctly.
Your recall went up. Your precision was already good.
Oh yeah, sorry. Yes. My bad. So my recall went up. I could identify all the 8 projects correctly, but then I have these false positives here, which means my precision took a
right. Yeah. So
this is when we
kind of tightrope balancing that
we did. And this is
so how did we solve this problem? I mean, what did we do?
Yeah. So this is exactly when we kind of realize that the way we are attacking this problem is maybe not right, because assume that where I have the project 10, 11, and 9 identified, okay, they are actually positions where company experience is present.
Right.
Or maybe skill set of a person.
Something else must be there.
Something else must be there, right? Right. So if I have put those offsets or rather those sentences or parts of the resume into those buckets, then they cannot be identified as project.
Right. Your chances of them being falsely identified would reduce if you have already identified as something else.
Exactly. So that's when we realized that this was not a two-way classification problem.
So it was a multi-way classification
problem. We had to attack all the buckets at once. We had to do a multinomial on this. That's when we realized this.
Okay, so just a time check. We are running like, we have just 5 minutes, and let's just quickly come to the results, and we will then take questions in the end.
Sure. So as we just saw that we are going to do a multi-way classification or a multinomial. So we did process all these resumes with 90 features, each every offset, and 8 target variables. We classified them, and we realized that using these 90 features, when we are classifying them, the smaller size target buckets were extremely accurate. That means the entities which are smaller in size, like the full name or the objective or the skill set, which are very small, like 2 or 3 lines, they are very accurate. But the ones which had a slightly longer content, like projects, overview, they were not really accurate. So what was the problem was with these things, with these entities rather, was that there were some outliers that were being sprinkled all across in the resume. So what I mean by outliers is that something like this. So if I have a project here at the bottom, okay, or the entire project block rather, which contains all the projects, I have some of these, smaller pieces of land which are occupied by my project label incorrectly. Now, what we realized was that why this is happening is because we have not considered the proximity. So when a project block is present in one place, it cannot be present in some other place. Right. Or when the length of the project block is so high, how can such a small block?
Yeah. So that itself could be used as a feature.
Yes.
What is how big the contiguous piece called project is.
Yes.
Whether it is 200 characters, then it is likely. But if it is 2 characters, very unlikely.
Very unlikely. So that's exactly what we used. And we ran a second pass of multinomial neural net algorithm with only these 5 or 6 features that we calculated from the results that we obtained from the first pass. And then we were able to identify overview, project, and footnote very accurately.
That's how it became deep learning. Like you had in the first pass, 97 of these neurons in the tensor, and then you have now 8 in the second pass.
Correct.
Right.
Correct.
Okay. Yeah. So
correct. That's how it became a deep learning exercise of how you solve a problem using deep learning. And in terms of, the numbers or the accuracy and the precision, the error rate at the offset level was only 12% in identification of each of the characters bucket or the entity. So that was the result that we got.
Excellent. So what were the tools that you used? So quickly, we have I think a couple of minutes.
Sure. So we used R as the basic machine learning and the deep learning kind of a tool set. And along with that, we used Gate, as we already talked about. Java in the background to do some amount of text processing, and also MySQL to store some data, which we ran into trouble with later on because MySQL does not scale well, and then we had to kind of remove it, and we just went with files dump on the hard disk. And we used algorithms such as logistic regression. So we started with the most basic machine learning algorithm, went up till multinomial neural nets, and that's when we found the solution that we were looking for.
Wow. So I'll give you 13 seconds to talk about your book.
Okay, thank you very much. So, so quickly to talk about my book. So this book, which was released in November 2017, Natural Language Processing with Python Cookbook, this is for beginners and beginners alone. Now, since the the hype around data science and natural language processing, a lot of people are a lot of fresh people, fresh graduates are trying to get into this field. So the idea why this book was conceived was, you can get the theoretical knowledge out there available on, the website of a Stanford, or you can go and do a Coursera course, or, any MOOC on Udemy or some other site, and you can get the theoretical knowledge. But what you lack is the actual practical hands-on knowledge. So this book helps you in your hands-on, how you practically do the things. So just to give a quick example. So you just tweeted about, recommendations for flights from, say, India to the United States of America. And immediately in the next page or in some other website that you're browsing on, you are seeing ads of, websites like Skyscanner, and some hotel related stuff and all that.
So all recommendations start
coming to you in ads section. So how does this come? So somebody out there is monitoring your Twitter account, Twitter handle. He identified this information, did some natural language processing, identified and understood that you're looking for flights. That means it is a ripe opportunity to throw these kind of advertisements at you. So this is what natural language processing's power is, and this is how it is utilized in the world today. And this is where the book that I have written is where you can start of your journey in learning how to apply natural language processing in real world scenarios.
Great. So thanks a lot, and I'll be talking a little bit about Synerzip, but I'll invite anyone from the audience would like to ask any questions. So Synerzip is a company headquartered in Dallas, and we have offices in Silicon Valley as well as in India. And about Synerzip, we have 500 plus professionals working with 110 plus product success stories. For 6 consecutive years, we were awarded the Inc. Fastest 5,000 growing companies, and we are, a co-development model with dual shore, with now close to 13 years in business, and what you can expect is 50% savings, and true agility is in our DNA because we started as an agile company. The different types of offerings we have is proof of concept, doing a lean startup with MVP, the hybrid model of offshore and outsource, and accelerating the product map, which is the most popular of our models. And of course, we also do QA as QA or migration as a specialized kind of offering. This is a bit about our dual shore operations, about the way we work together, the US team as having customers and architects working synergistically along with our India team of product owners, developments, QAs, DevOps, UX professionals. So that's the list of clients. This is not completely exhaustive. This is just a representative. There are 100 more clients which are not there on this slide. So talking about the next webinar, it's going to be a webinar on React, and this is going to be done by Yogesh Patel, who's an author and director at Synerzip. He's director of engineering. So is React the best thing since sliced bread? And believe you me, Yogesh believes that it is. So we'd like to hear from Yogesh why React is the best thing since sliced bread. So with that, let me check if we have time for questions, and if there are any questions. I think we have, let me check. Yeah, so I think we are quite running out of time. So we will take questions offline, and we would probably respond to them in our channels like the social media. We are on top of the hour. It's already 2 minutes past. So thank you, Krishna. Thanks for your wonderful insight into deep learning. I hope all the listeners enjoyed your insights and your takeaway as to what not to do and how not to get trapped in a conversation on birthday surprises. Thank you very much, Krishna, and thanks audience for attending today's webinar.
Thank you, Vinayak. Thanks a lot.